Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element actinium. Since no one has ever made a visible chunk of this element, our stand-in here is the thorium-rich mineral vicinite. As we'll see, thorium can decay into actinium, so this sample probably contains a bit of this element. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Actinium is the 89th element in the periodic table. Its atomic number is 89 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Wherever you find uranium, you find a tiny bit of actinium. Uranite, also known as pitchblende, is a radioactive, uranium-rich mineral and ore with a chemical composition that is largely UO2, or uranium dioxide, but because of oxidation, also typically contains variable proportions of U3O8, triuranium octoxide. Carnotite is a potassium-uranium vanadate. You can see the uranium in their chemical formulae. Radioactive decay of the uranium causes both of these minerals to contain a small trace of actinium. More on this later. 1 ton of uranium ore contains about 0.2 milligrams of actinium-228, so these are not mined for their actinium content. As we'll see, actinium is most often manufactured. Still, uranium ore is important in actinium's discovery. A little pre-actinium history first. Marie and Pierre Curie discovered radium in 1898 after concentrating and purifying 10 tons of the uranium ore pitchblende. It took more than 3 years, and their effort was rewarded with an almost invisible stain in the bottom of an evaporation dish. That stain was only 1/10 of a gram of radium chloride. The highly radioactive radium ionized the air above it, creating a ghostly blue glow when the lights were off. The Curies left behind other residues when purifying their radium. These residues of the pitchblende extraction process were explored by another French chemist who worked with the Curies, André-Louis. He announced the discovery of a new element in 1899, which he named actinium. He may have been premature in his announcement, probably having seen the element protactinium, element 91. He also changed his mind on his results several times, but he's still given credit for the discovery, since he probably had some actinium in his sample. In 1902, Friedrich Geisel independently found a radioactive substance he thought was similar to lanthanum. He called his element emanium, after the radioactive rays emanating from the sample. It's more likely Geisel was the actual discoverer of actinium, but he's rarely given the credit. The discovery of actinium was put on more solid ground in 1904 and 1905 by Harriet Brooks, Otto Hahn, and Otto Secur. Harriet Brooks, a Canadian physicist, also studied the mysterious gas given off by thorium, which turned out to be radon. She was one of the first physicists to establish that radioactive elements can transmute from one element to another, something alchemists were looking for, but never found. The name actinium originates from the Greek actus or actinos, meaning beam or ray from the radioactive particles radiating from the source. Actinium is, not surprisingly, a member of the actinide series of elements down at the bottom of the table, and in fact gives the series its name, being the first element in that row. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides are radioactive. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 89 protons for actinium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 34 known isotopes of actinium, and we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of actinium are radioactive. As we'll see in the next slide, all the half-lives of actinium isotopes are fairly short, but long enough we find them in nature as decay products of other radioactive elements. More on that in a couple slides too. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of actinium occupy the same place in the periodic table. Of the isotopes of actinium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest actinium half-life is actinium-227, with a half-life of 21.772 years. Because of its short half-life, actinium is, gram for gram, about 150 times as radioactive as radium. All the natural actinium, mostly actinium-227, is a daughter product of decay from higher up in the periodic table, and actinium is constantly created by radioactive decay. More on this in a bit too. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If we wait 1 half-life, half of the isotope will decay, and we'll have 512 atoms left. If we wait 1 more half-life, half of that decays, leaving us with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms. And so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice there's 1 remaining atom after 10 half-lives. If we waited 1 more half-life, our remaining atom would have a 50-50 chance of decaying in that time. I've mentioned that all actinium is from radioactive decay of other elements. Let's look at that. I want to show you some of the decay series that lead to actinium, and I want to do it on a chart you'll see in many physics texts. We're only using a very small portion of a much larger chart. On this chart, the horizontal axis shows how many protons plus neutrons are in the nucleus. This is related to the atomic weight of the isotope. The vertical axis is the number of protons in the nucleus, its atomic number. Since the atomic number also tells us which element we're dealing with, each row is one unique element. Generally speaking, when an isotope decays, it can do this by emitting an alpha particle or a beta particle, and I'm oversimplifying this. An alpha particle is made up of 2 protons and 2 neutrons, 4 particles in total. So if we start with something like radium-226, it has 88 protons. All radium isotopes have 88 protons. Radium-226 decays by alpha emission, meaning it loses 2 protons and 2 neutrons, 4 particles in total. This means we need to move 2 rows down for the 2 protons and 4 rows to the left for the 4 total particles. You can see we arrive at radon-222. Okay, this is the move for alpha decays. What about betas? Here, one of the neutrons in the nucleus becomes a proton and an electron, and the electron is spit out of the nucleus as a beta particle. This means the nucleus gains a proton, but does not change its atomic weight significantly since electrons are so light. This time, we'll start with thorium-234. Gaining a proton, but not changing atomic weight, moves us up 1 row, and we now have a new element, protactinium, but with the same weight, 234. This is what beta decay looks like on our chart. Now, let's look at a complete decay series. Natural uranium is mostly uranium-238. A small portion, only 0.7%, 1 out of every 142 uranium atoms, is the isotope uranium-235. This is our starting point for this decay chain. Uranium-235 has a half-life of 700 million years. It decays by alpha into thorium-231. Thorium-231 decays by beta, remember we move up 1 square for betas, into protactinium-231. That decays by alpha into actinium-227, the longest-lived actinium isotope. This decay series is often called the actinium series, so as not to confuse it with the uranium series, which starts with uranium-238 we saw in the previous video about radium. Just to complete the decay chain, the actinium-227 can decay 2 ways. 98.62% of the time, it decays by beta to thorium-227, a different isotope of thorium than we saw before. But 1.38% of the time, actinium decays by alpha into francium-223. The francium decays by beta to radium-223, but our thorium-227 from before decays by alpha to radium-223 as well, giving us 2 paths to this element. Radium-223 decays by alpha to radon-219, which decays by alpha to polonium-214, which decays by alpha to lead-211, a radioactive isotope of lead, which decays by beta to bismuth-211, which decays by alpha to thallium-207, which finally decays by beta to lead-207, which is non-radioactive and stable. That was a roller coaster ride. There are other decay chains which account for other actinium isotopes, one of which I'll show you in the next slide. This decay chain results in another common isotope of actinium, actinium-228, with a half-life of 6.13 hours. It starts with thorium, specifically thorium-232, with a half-life of 14.1 billion years. I won't bore you with the details, but you can see this chain contains actinium-228 in red, which continues to decay down until it reaches the endpoint of lead-208, another stable isotope of lead, different than we saw before, which was lead-207. Naturally occurring lead comprises 4 isotopes. 1.4% of naturally occurring lead is lead-204. Lead-206, found at the end of the uranium-238 chain, accounts for 24.1% of the lead we find naturally. Lead-207 accounts for 22.1%, and lead-208 accounts for the majority at 52.4%. In this and our previous episodes, we've seen elements created as daughter products of other radioactive elements. We've seen the series that started with uranium-238, uranium-235, the Actinium series, and one that began with thorium-232. In this episode, I'm going to introduce one more, the Neptunium series. Here, we start with Neptunium-237, a natural byproduct of uranium decay and, more commonly and abundantly, a product of fission in nuclear reactors. I've put the isotope, its decay mode, and its half-life on the screen for your reference. Neptunium decays by alpha into protactinium-233, which decays by beta to uranium-233. This decays by alpha to thorium-229, which decays by alpha to radium-225. Finally, the radium-225 decays by beta to actinium-225, this presentation's element. Of course, it doesn't end there. Actinium decays by alpha into francium-221, which decays by alpha into astatine-217, which decays by alpha into bismuth-213. Bismuth-213 can decay two ways. 2% of the time, it decays by alpha to thallium-209, which decays by beta to lead-209, a radioactive form of lead, which decays by beta to bismuth-209. Returning to our bismuth-213, 98% of the time, bismuth-213 decays by beta to polonium-213, which then decays by alpha to lead-209, which, as we've seen, decays by beta to bismuth-209. Finally, the bismuth-209 decays by alpha to thallium-205, which is stable and not radioactive. This is the only decay chain we've seen so far that does not end in a stable lead isotope. Since we're on our sixth radioactive element, seventh if you include bismuth, I'd like to repeat how radioactivity is measured. There are three interesting facets of radioactivity we should pay attention to. First, we might want to know how many disintegrations per second a given source gives off. This is a measurement of its radioactivity and is the simplest thing to measure. You can use a simple Geiger counter and just count the number of detections per second, but you need to take into account the size, area, and the distance of the detector from the source, and multiply the measured counts per second as if your detector could completely surround the source to catch all the disintegrations in every direction. The international unit for this is the becquerel, named after the discoverer of radioactivity, Henri Becquerel. 1 becquerel equals 1 disintegrations per second, so most sources are in the kilo, mega, or even gigabecquerel range. In the US, we also use an older unit, the Curie, obviously named after our dynamic duo, Marie and Pierre Curie. 1 Curie is the amount of radiation given off by 1 gram of radium, discovered by them, get it? 1 Curie is 37 billion disintegrations per second, or 3.7 times 10 to the 10th becquerels. Now, radiation carries energy, and that energy is deposited in your body or into any object the radiation hits. The next unit measures how much energy is absorbed per kilogram. This is called the absorbed dose. In the metric system, energy is measured in joules. 1 joule is the amount of energy used to lift an apple from the floor to a table. The international unit for absorbed dose is the Gray, named after Lewis Harold Gray, a physicist who worked on the effects of radiation on biological systems. A Gray is equivalent to 1 joule of energy absorbed per kilogram. This is quite a bit of radiation, so you'll usually see units of milligrays or micrograys or something like that. In the US, we've used a unit called the Rad, or Roentgen absorbed dose, which is 1/100th as large as the Gray, but still a large amount of radiation. Roentgen discovered X-rays in 1895. Lastly, we want to know how this absorbed energy will affect you, and that will depend on the type of radiation. Alpha, beta, or gamma, which bodily organs are exposed, and how sensitive these body parts are to the specific kind of radiation. This is called the effective dose. The units here are the sievert, named after Rolf Maximilian Sievert, who was a medical physicist. He studied the biological effects of ionizing radiation. In the US, we also use the REM, which stands for Roentgen Equivalent Man. The sievert is just 100 rem, and the rem is 1/100th of a sievert. These are human health-based units. They take the absorbed dose and adjust it as an indicator for the potential for long-term health effects, such as cancer, genetic damage, etc. The effective dose is used to set limits on exposure for radiation in the home and workplace. For instance, you are allowed to be exposed to 50 millisieverts, or 5 rem, per year in the workplace. You normally absorb about 67 millirem every year from the environment around you. That's 1/75th the allowed annual dose. A dental X-ray exposes you to about half of a millirem. A standard chest X-ray, front and side, exposes you to up to 10 millirem, and a chest CT scan gives you up to 800 millirems. Although radiation exposure always carries some risk, with medical X-rays or CT scans, the benefits always outweigh the risk. I normally talk about the abundances of elements on this slide, but because of the short-lived radioactive nature of actinium, there's not much to say here. There's really none to speak of in the universe, having all decayed away by now, and none in the sun for the same reason. Likewise, none in meteorites, and not enough in the Earth to talk about except for the tiny amount resulting from the decay of other elements. More on this later. It's absent in the oceans, and, of course, thankfully, there's none of it in us. That was a lot of red X's. Estimates are that at any given moment in the crust of the Earth, there's around 14,000 metric tons of actinium. This amount is constant. Just as much is created as decays. The most common isotope, actinium-227, has a half-life of 21.772 years. This means that every 21.772 years, we lose 1/2 of that 14,000 metric tons, which is then replaced by radioactive decay of other elements. Per year, about 644 tons of actinium is created. Uranium ores from the Democratic Republic of the Congo and Canada are richest in actinium, mainly because they're richer in uranium. But none of that matters. As I mentioned, actinium is manufactured rather than mined. There's too little actinium to make mining it profitable. More on that in the next slide. If you could magically mine that new 644 tons created each year from the entire Earth, you'd have a cube about 316 centimeters, a little over 10 feet on a side. Compared to a human, that's minivan-sized. I mentioned actinium is 150 times as radioactive as radium, gram for gram, and also 1 gram of radium undergoes 37 billion disintegrations per second, or 1 Curie. We have here 644 million grams, each of which is 150 times as radioactive. This is enough heat energy to power almost 350 homes. Aside from making the air glow blue from the radioactivity, our cube would become extremely hot, rather unfortunate for our comparison person. I already stated that actinium is manufactured, not mined. The isotope, actinium-225, is created using a cyclotron accelerator, like the one you see here. You start with an atom of radium-226. I'm only showing you the nuclei since that's where the action takes place. You then take protons, which are really hydrogen nuclei with the electrons stripped from them, and accelerate them to smash into the radium. A successful hit, and those are rare, results in a nucleus of actinium-227. This unstable atom almost immediately sheds 2 neutrons and becomes actinium-225 with a half-life of 10 days. This method was first used in Germany in the year 2000. The other way to manufacture actinium is to refine it from spent nuclear fuel pellets. This means first separating the uranium-233 from the fuel. This uranium then decays by alpha to thorium-229. The thorium-229 is separated from the uranium. This thorium decays by alpha to actinium-225. The slightly actinium-enriched thorium-229 is milked, their term, not mine, for its actinium content. This is a purified sample of actinium-225 nitrate produced at Oak Ridge National Lab's Radiochemical Engineering Development Center. Notice it glows blue when the air surrounding it is ionized by alpha particles emitted by the highly radioactive actinium. Given its rarity, it's really hard to attach a value to actinium since it must be manufactured, and the raw material is difficult to get. One source I ran across places the value at a blistering $29 trillion per kilogram. Of course, no one will ever see a whole kilogram. It's manufactured in milli or microgram quantities per year. That means it would take over 1 million years to make a kilogram. Actinium has a density of 10.07 grams per cubic centimeter. As a reminder, the density of water is 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds. You can see it's a bit denser than bismuth at 9.78 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, actinium's density is 10.07 grams per cubic centimeter, a touch lower than silver. It's not practical, or possible, or wise to own a block of actinium, so I'll use my lead block to substitute. It's just slightly denser. Actinium has a melting temperature of 1050 degrees Celsius, or 1922 degrees Fahrenheit, which is the 47th highest melting point, about in the middle of our chart. Actinium boils at 3200 degrees Celsius, or 5792 degrees Fahrenheit, giving it the 30th highest boiling point of all the elements. That's about 2150 degrees Celsius above its melting point, giving it the 20th largest liquid temperature range of all the elements. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range, all the way down to neon, which is liquid only in a 2.51 degrees Celsius range. Actinium has the 16th widest range at 2,150 degrees Celsius. Notice all the noble gases and hydrogen have very small liquid temperature ranges. I've had to estimate the size of the actinium atom since no accurate size has been determined. If we compare the size of the actinium atom to that of hydrogen, we'd see something like this. The actinium atom is about 4.8 times the size of hydrogen. Here's the electron structure of actinium. By the way, a picometer is a trillionth of a meter. Atoms are majorly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium, at the top left, to smallest, helium, at the bottom right. The size of actinium places it in the upper region of the chart, maybe around the third largest atom, about the same size as barium. Although I've been able to tell you some things about actinium, if you look at tables of data about the element, you'll note there's simply a lot we don't know about it. Notice all the N/A's, meaning the data is not known or not available, mainly because no one has collected enough of it to do any bulk experiments, and the fact that it's dangerously radioactive in those bulk quantities. This table is from Theo Gray's periodictable.com. Lots of info there. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of actinium. Let me enhance the contrast a bit to bring out the specific colors excited actinium gives off. Not an overly complicated spectrum, but it has a good variety in the reds through the violets. Spectra of the elements uniquely identify them to scientists, as each gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. Aside from research applications, there's not much to say here. The only current application is an experimental cancer treatment using the short-lived actinium-225. Remember, actinium is difficult and expensive to produce, only recovered from nuclear reactor waste or synthesized directly using an accelerator. Part of the difficulty is its short half-life of 10 hours. Once made, you have to get it to the patient quickly. This is a 17 millicurie sample of actinium-225 nitrate produced at the Oak Ridge National Lab. They're trying methods to increase production of this isotope because it's still too scarce to use widely as a cancer treatment. Here's how that treatment works. The treatment is called targeted alpha therapy and is currently under heavy research. We start with a nasty cancer tumor. The researchers design a targeting molecule that's keyed to bond only to the cancer cells of the tumor. They build into the targeting molecule a special receptor called a ligand that will also bind and hold our actinium atom. Once in the body, the targeting molecule and its radioactive actinium binds specifically to the cancer cells and delivers its radioactive dose specifically to the tumor and not generally to the entire body, sparing healthy tissue. The short range of alpha particles is a real advantage here. The actinium is only the beginning of the chain because there are a variety of daughter isotopes that also emit alphas. The actinium decays by alpha into francium-221, which decays by alpha to astatine-217, which decays by alpha to bismuth-213. Bismuth-213 decays by beta, emitting an electron to become polonium-213, which immediately decays by alpha to lead-209, which is still radioactive, and with one final beta decay, we reach bismuth-209, which is stable. 4 alpha particles and 2 betas for the price of 1 actinium atom, all delivering their damaging radiation directly to the tumor, hopefully destroying it without harming healthy surrounding tissue. This treatment has reached clinical trials. Actinium obviously serves no known biological purpose, so you'll find none of this element inside you. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about actinium. Captain of the boys, banished to the bottom of the bench, troublemakers all. In the next program in this series, I'll examine thorium, the next very abundant element of the actinides, with a very long half-life. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element actinium.